Dialing in everyone from, I guess, all over the world and all sorts of different time zones. My name is Jimmy Bogard, and you can find me on Twitter at @jbogard. This presentation and as well all the code and examples are on my GitHub at github.com/jbogard. And I blog a lot about this topic and a bunch of other stuff. I blog at jimmybogard.com. A little bit about myself. I'm an independent consultant, also the acting chief architect at Headspring, an independent consulting agency out of Austin, Texas. I do a lot of open source stuff, and I think they give me the MVP award for it now, but they don't really say, so yay, I guess. And yeah, this is a fun topic for me because I've been having to deal with this problem for, I guess, almost 15 years now, the problem of distributed tracing. And for as long as I've had to deal with distributed systems, I've wanted to know like what the heck is actually going on behind the scenes. And over my career, I've had to build distributed tracing infrastructure from scratch at least twice. And while it is like a fun project, and it's infrastructure, so you're your own product owner, and you get to make up all your own features, and it's fun to do. Like my clients don't care about that; they just want it to work. And so sometimes I don't have the time or money to be able to implement my own distributed tracing. But in the last couple years, 2 or 3 years, distributed tracing has now become much, much easier to implement and put in place in your applications. So in this hour, I wanted to show what I've been doing in the past year or so with the client putting in distributed tracing in a very complex microservices kind of environment because, microservices, yay. So for a good part of my career, I was just dealing with like single process, single application kinds of systems. Those could get pretty complex, right? They're desktop or web applications, but the entire application is basically in one single process. Now, what that means though is that if something were to go wrong in this process, an exception gets thrown or something like that, then you get this nice thing. This is a stack trace. And the stack trace tells me exactly where in my code the exception occurred. But not just that location, it also shows a stack of all the calls leading up to wherever I found that exception. So for a lot of my career, like this is all I really needed, right? Like something goes wrong in my application. I see the exception. I can see exactly what methods were called. And if I'm debugging as well, then I can go see like, well, it was past these arguments over here and these arguments over here, and trace that all the way back up to the entry point of the application. But this works for like everything inside a single process. It works fantastic, right? I just got the entire trace and stack is in memory. So I'm able to walk back up the stack and figure out exactly how you got there. But these days, my applications I deal with aren't so simple. They're more complicated. They're multiple applications talking to each other using various kinds of protocols. So in my application, if the user hits some API from the front end, but the exception is way over here in the back end, well, the exception stack trace is in that application way down in the lower right-hand corner. And the top part of the application and the API, I don't necessarily see any of that information. I just see, some kind of API exception that occurred, but otherwise the stack trace ends in the API and doesn't peek through into the other downstream systems. So me as a developer or SRE trying to figure out, okay, I got this exception in my logs, how did this happen? And what are the sequence of calls that led up to this specific exception happening? I don't have a lot of options available for me. For a lot of my career, what I would do is just spit out log files. And so if I wanted to figure out what went wrong in that log file, I would look for that application's logs and then try to correlate back to the logs from the other service and correlate logs back to the other service. And maybe I can enrich those logs with things like contextual identifiers, like, well, is this user ID under this session identifier? But still, it's like all these different logs from all these different places that are very difficult to correlate together. And even if you dumped them all in one location, it's just a big haystack that you're trying to piece together how the needle fell into it to be able to diagnose what the heck was going wrong. So in one of my first really big distributed systems I worked with, we thought we had a great idea, which is, okay, what I'd like to do is be able to correlate some of these calls together. And if time isn't good enough, like the kind of timestamp from one to another, that's not accurate enough. We need something a little bit better. So what I really need to know is when system A is making a call to system B, that in that call that I'm making, I need to pass some kind of correlation and information so that in system B, it's able to look at that incoming information and say, aha, in my log files, I'm not just going to put my identifiers, I'm also going to include the upstream services identifiers as well. And so that's really what distributed tracing is intended to solve. It's able to piece together or put Humpty Dumpty back together again by including context correlation identifiers through every single communication between different services. And then when those individual services need to report out information about what's going on, they don't just include information about that service, but they also pull in a contextual identifier that they've received from their upstream service. And with this kind of scheme in place, then system A calling system B will include a context identifier, and then system B including that context identifier in their logs, then something that's collecting all of these logs can start to put all these different identifiers together in order to present basically like a linked list or a graph, directed acyclic graph of all these calls being made to all these different services. Kind of like a Git source control history view, that you want to see all these different calls linked together. So this is, fun to build, I guess, because you have to figure out, what should the headers be of all this piece of information? What should the identifiers look like? And so some very large companies that build these kinds of systems said, okay, right, this is really nothing to do with our core business, so why don't we do the altruistic thing and open source it instead of selling it or whatever? And so some companies did that. One good example of that is Zipkin. Zipkin's a very popular distributed tracing utility. It's free, you can run it in your own box. It doesn't require a lot of resources to get up and running. And what they've done is basically two things. One is provide a standard for what those identifiers look like as it goes from place to place to place. And they include a couple pieces of information. One is just the identifier of this one individual operation. That's known as a span ID inside Zipkin. And then the thing which I didn't show here is a way to link all those different calls together, some kind of global identifier for all those different sub-operations and components. And that was known as a trace ID. So with a trace ID and a span ID, you get all the logs together of one specific global operation. And then the span IDs give you the linking of how call A is correlated with call B. So Zipkin includes this scheme of headers flowing through your system. And so you still have to have something needs to put those headers in as I make calls from place to place. So you still have to do that. And the other thing you need is okay, so I have the span ID and I've got the parent span ID. What do I do to be able to get that information? So these spans need to be reported to something. So what do I report those spans to? So what I could do is, as part of my Zipkin application, what they have is an API that gets called. So every time you have a span or operation completed, then what I can do is then call that API to say, hey, I've got some span information. And so Zipkin provides a server to receive those spans. And the last piece of the puzzle is, well, you got to see this stuff. And so Zipkin also provides a user interface to be able to show and search for individual traces. And so distributed tracing is one of the three pillars of observability, the other two being logs and metrics. You can't just have logs, you can't just have metrics. You need all three to have that kind of complete picture. So distributed tracing for me really completes the other two pictures of, well, how the heck did this thing happen to be able to get to this point? So not necessarily even exceptions. If there's some customer journey that happened, how do those different pieces get pulled together? So Zipkin came out with their application, became super popular, and then other companies started to adopt this individual standard. But there wasn't just that standard, there were several other standards as well. So other tracing utilities had their own identifiers, like Microsoft Application Insights had their own identifiers, and pretty much any distributed tracing visualizer on the market had their own custom spin on this. And as the KCD comic goes, what happens when you have N standards in different implementations? You make another standard, which is now N+1 implementations. And so that's what some folks from a lot of different companies did, to get together and say, let's build one single standard for all these different ways of doing these kinds of tracing identifiers flowing through the system. And so that's what the W3C did. That does a lot of different standardization efforts. They said, let's get together with some folks from tracing tools and hosting providers and other distributed tracing tools, visualizers as well, and collectors and application service providers too, and said, let's get together and decide on a good standard for how do we show this, how do we trace this information through. And so that's what the W3C trace context standard is all about. Now, this was just finalized early this year, like February. It was finally taken out of draft mode and into like ready to go mode for that standard. And it describes a way of formulating the identifiers, how to format them, and then ways and behaviors of how different systems should behave when they receive this tracing information. Now, the next piece of the puzzle was Microsoft in the .NET Core world. So this is distributed tracing made easy with .NET Core. Well, .NET Core and .NET has had diagnostics for a very long time. And that API was really customized for a lot of the Microsoft environment. So it didn't really jive with this overall standardization support. So as part of the W3C trace context effort, Microsoft shifted their development of their diagnostics APIs to now support these kinds of standards out of the box. So that's the other part I'll be showing today is the APIs inside of .NET Core to support these kinds of standard tracing support. So the identifiers that flow through the system, this is coming from the activity API, and then the IDs that are transported on the wire across services are done through a special header called the trace parent header. So you can actually inspect your traffic today, and you'll probably see that for a lot of your traffic because it's starting to be turned on by default in a lot of systems these days. Now, this W3C standard was really described for HTTP traffic. So if I have services that use APIs, web APIs to talk to each other, that's what that was all about. They also had some extensions for gRPC to have some more compact identifier support. So where gRPC, like the size in the wire really matters, they shrunk down those identifiers for those kinds of communications over the wire. But the systems I work with don't just deal with gRPC and HTTP. They deal with a lot of messaging as well. And so with messaging, it's still a kind of communication going over the network. It just happens to be durable and written down as opposed to HTTP, which is more of a stateless protocol. So with that, we have to figure out, well, what do we need to do for those kinds of systems? When I have an API calling a service, but then that uses RabbitMQ, then how do I extend my system to be able to include the right context information on communications going out the door? And when I receive communications, how do I ensure that it correctly sets the current operation identifiers so that if any other call is making out the door, that the context is correctly flowed through? So we'll be looking at that today as well. Now, the W3C trace context standard is really about that identifier on the wire and how to deal with it whenever you receive it. But it doesn't say anything about what to do with that information. So if I just had that trace information, I guess I could still log it out to disk, but that's boring and really difficult to deal with because now I just have all these identifiers and log files that I have to, again, Humpty Dumpty back together again myself. Not the most fun thing in the world to do. So that last part is a new emerging standard to be able to try to standardize on the collection of that information. And I really noticed the problem when I was trying to put in distributed tracing with a recent client. And they didn't know yet what tracing tool to use in order to visualize their traces. So we looked first at Zipkin. Zipkin has a lot of extensions for .NET Core-based applications and a ton of other different platforms as well. But if I am a product company that's wanting to build infrastructure plugins for tracing tools, then I have to build one for Zipkin. But there's like a dozen of these on the market, these distributed tracing tools. So when the next one comes around like Jaeger, then I would have to develop these kind of API calls into this different tracing tool as well. And so a new effort came into play of not just trying to standardize on the communication between services for these tracing calls, but also recording of the traces as well. Because just communicating the information between services is just one little, that's just kind of table stakes to be able to even do distributed tracing. But then to report on it, I don't have to support all these different kind of tracing models. So that's where the OpenTelemetry project comes into play. So in addition to standardizing on the communication, OpenTelemetry strives to standardize on the reporting of logs, metrics, and traces. Now, for a lot of platforms, they don't have any kind of clear standard on how to do these sort of things, but some do. Like Java's ecosystem has a very well standardized way of dealing with logs. They don't necessarily have a great way of dealing with traces. So OpenTelemetry steps in and says, okay, we will define the APIs for what this collection should look like and these object models should look like. And then all these different collecting and reporting utilities just need to go off that common model in order for them to be able to be plugged in and work. So with these pieces in place, OpenTelemetry really pushing towards a standardized API and the standards between the different communications and services now makes it really easy for me as an application developer to turn on distributed tracing and be able to visualize it easy without having a lot of vendor lock-in to say, well, we picked Zipkin, so that's what we got to do now because some architect somewhere decided that was the way to go. Now, I will say that one thing that is a little different in the .NET world than other platforms is .NET already had an API in place for reporting operations and traces, and that's that activity API. So the folks from Microsoft and the folks from OpenTelemetry really wanted to have kind of the best end user experience. And so what the team decided to do is, instead of making this entirely new API to the side that would require them to throw away everything they've done so far with any kind of tracing whatsoever, instead what they've done is move the existing activity API to support the OpenTelemetry model. Now, the downside is the names don't exactly match, so it's called an activity versus a span. They can't really do anything about that. But that also meant that it was a much faster way for them to get there without having to go through and just kind of replace all this existing code that has worked for years and years and years and be very difficult to upgrade in place. So we'll be doing in a demo in a couple minutes here. We'll be showing the activity API for W3C trace context propagation. We'll also be looking at how to include additional user or machine specific information to ensure that information finally shows up on the actual tracing information at the end. I'll be looking at the OpenTelemetry for activity adapter. That is the piece from OpenTelemetry that plugs into what the activity looks like. And then finally, we'll look at Jaeger and Zipkin as our OpenTelemetry exporters, all in .NET Core 3.1. I wasn't quite brave enough to go to .NET 5 RC2, which released 3 hours ago. Not quite that brave, but I will be showing what you'll need to change when you move from .NET Core 3.1 to .NET 5 when it drops next month in order to get this to all continue to work. So first up, let's just look at some basics of the activity API. And one of the reasons why I think this is important, the underlying activity API, is if you want to enrich your information that shows up in your traces, you're going to need to know how to deal with activities. So let me swap over to the old Visual Studio. Not the RC, this is just stock Visual Studio. And let's just see if we can make this application break. So if I were to have a method here, public void static, I do something, and this threw an exception, load up. Now, if I call do something from right here, then of course, I would throw an exception. I would get a stack trace, and it would tell me exactly where that exception occurred. Now, let's suppose that this do something method was not in my code, but was in someone else's code, and then I consumed that code from inside my application. And if something went wrong, I wanted some more insight into what was going on there. Well, what typically would happen is you would, in that consuming application, that consuming code, you would have logging statements inside of there. And Microsoft has created the iLogger of T interface to provide a standard way of doing logging inside of systems. However, if this do something method is not in this application, but is somewhere else completely, then how do I make sure that whatever I'm doing here, I can still see what's going on over there? And that's really where the activity API comes into play. So the first thing we do is we'll say var activity equals new activity, and we need to give the activity an operation name. Now, this sometimes is the method name, sometimes it's just the name of the logical operation that's happening. It could be like running application. And before this interesting operation happens, then we need to start our activity. So we call activity.start. We do whatever interesting operation we're going to do. And then the last thing we do is stop the activity. Stop. Okay. When my activity is stopped, we do get interesting information as part of it. We get the duration as a timestamp. So if we're trying to get some metrics about what our system is doing, that's kind of like a stopwatch in order to say this operation took this long to do. So what about in this do something method? I'm going to get rid of this exception because that'll look ugly. So I'll just do console.writeLine do something. Now imagine this line of code is somewhere else completely. And I need to provide some contextual information to this method so that it knows where it's been called from the outside world. Now, inside this do something method, we want to do the exact same thing we did before. Let's say var activity equals new activity. Call it do something. And we'll do the same thing, activity.start. And that stop. Okay, now I'm gonna put some breakpoints in here just to see what we see. So I will put a breakpoint right here when we call do something, and then we call activity.stop. And then we'll put another breakpoint right here and right here. Okay, so as we go through, it will instantiate the activity, start it, call the other method, and then the other method will call that activity.start as well. So we'll say activity.start, and then if I look at the activity information, we'll notice that the activity has been given now an ID. And ID looks gobbledygook, right? It's like a pipe character with some hexadecimal, alphanumeric junk. It's probably some matrix code there. I have no idea, but it's calling inside of there. I'll go ahead and continue. Now that this activity that's not been started yet, if I look at it, we'll notice that it has no ID as part of it, just has the name. Now if I hit F5, after we start, let's go take a look. Okay, it's got an ID, but let's scroll down a little bit. I also notice that it has a parent ID, and that parent ID is the ID of the previous activity that we had in the other method. It even has a reference to the parent activity, so I can go activity.parents.id. But how did it do that? I didn't pass the activity through. Like I didn't give it the activity, just like I said activity.start, and it just kind of magically knew that there was an activity around to connect it to this activity that got started. So this is one of the key things that these tracing tools have to do is I need to be able to, in my code, somehow flow context between different operations so that when I report on them, I'm able to say, like, this is my parent operation to be able to link those things together. So depending on my platform, it achieves it in different ways. And the way that this platform does it, .NET Core, is with a special, very special property on the activity class called activity.current. So on the activity type, there's an activity.current property. That's a nullable property, so there may not be an activity. And what that is an async local static property or static field underneath the covers that's able to be shared across any thread of code that's sharing the same async context. So in an ASP.NET Core application that shares the common async context, that activity.current will continuously be updated whatever async local context I'm working with. Now, some applications and systems, they don't have that available to it. So instead of trying to rely on that thing, they'll just stuff it in some collecting variable parameter that goes through the infrastructure. But anytime I call activity.start, it will update that current with the new current and then connect the parent to whatever that current is. I did this because I was so curious. I looked in the code like, how's this magic working? And that's just all it's doing. You know, I have a new activity called start. I set the parent equal to the current activity and then set the new current to the new activity, and I'm good to go. Now, those IDs, though, you notice were not the greatest looking. They're pretty ugly. And so what the next thing we want to do is use this new W3C standard for our identifiers. And so to do that, it's a little bit wonky in .NET Core 3.0 and 3.1, but it works. And the way we do that is at the very beginning, we say activity.defaultID format equals, and I have a choice, hierarchical, unknown, or W3C. The other two we don't want. W3C is the one that we do want. So that's the W3C trace context format. And something we also tend to do in our systems, activity.force default ID format, just to make sure that if someone fiddled with this, we would get the one that we just set. So now let me run this again and see how our IDs look different. And when we see them, we'll see some additional information that we didn't see before. In my activity, we'll see that the format of the ID is a lot bigger. It's like 00 dash gobbledygook dash more gobbledygook dash another couple numbers at the end. So this format is actually, defined in the W3C trace context standard. And inside of that whole ID, we have a few things going on. We have the ID of the operation or the span, so the thing that's happening right now. We also have the ID of the entire trace. That's the second part we see there, the 4BD whatever. So that is common across all operations that are connected with this initial activity that started. And then I can also have individual operation numbers, and so that's what those numbers are at the end, which typically don't get used in my systems, but are possible. They're part of the standard. So in the next application activity I start, what we'll notice is that some of the numbers are much different. So at the end here, the ED4C, that's very different than 4DB. But the first part, which is the trace identifier, is going to be exactly the same. And this is so that collectors of this information can quickly index individual traces for all this reporting of spans coming in over the wire. Okay, so now I have a way of providing activity operation information inside my running application. Well, the next thing we need to do is be able to propagate that information out the door. So that is, when I make an API call on .NET Core application, I want to make sure that that trace identifier actually flows out to the other side. And then on the consumer side, when I receive that API call, if that incoming API call has that header in there, I want to make sure that I set that as my new activity parent ID. And you can do that. I can say activity.parent ID equals hello NDC Sydney. Oh, you could do that. Probably want to use an actual standardized format for that, but you can certainly do that. Oh yes, I have to say set parent ID, but you get the idea. I can set the parent ID to anything I want. So in infrastructure inside ASP.NET Core, they do exactly this. For incoming ASP.NET Core calls, they'll check the header. If that header exists for that W3C standard, then they will set the parent ID of this current activity for this ASP.NET request. And when they make calls out the door using HTTP client, they'll do the exact same thing in reverse. They will set the trace context identifier on the header as it goes out the door. So let's go back. That was just the activity basics. That's useful for when we want to have our own operations and spans that we want to report on. The next thing I want to show is OpenTelemetry, which is going to be the piece that consumes those activity events to do something interesting with them. Now, the activity API does have a way to report on that information, but the API kind of sucks. Kind of sucks a lot, actually. So when I call activity.start, that can raise an event for that information. And that information event actually comes through a new API called a diagnostic listener. So typically what you have is a static diagnostic source source equals new diagnostic listener. And then the name of the diagnostic listener is going to be the same name as your activity. Okay, so the activity objects themselves don't have events I can subscribe to. Instead, what we have is, instead of starting activity just like this, what we'll do is we'll say source dot start activity, passing in the activity. And we can also pass in context. I'm not going to pass in anything. So what this will do is start the activity and raise a diagnostic event so that something can subscribe to that and then act on it if they want to. And the way I can subscribe to that diagnostic event is that there is a diagnostic listener dot all listeners. That is an observable of diagnostic listener. And I could say subscribe to this observer diagnostic listener, which also has events that give you the start, stop, and exceptions for activities. But I don't know, like observables are fun and all, but they're kind of a pain to deal with in your infrastructure code. So what OpenTelemetry will do is kind of encapsulate all these different pieces for you, so they don't have to have these observables and subscribers, and just say, here, just implement this class, tell me the name of the activity that you want to listen to, and here's a method that I will call whenever that thing happens. So I've got a slightly more complex application than what we just saw to try to give you a little bit better illustration about, in a more complex distributed system, how these different calls get pieced together. So I have a microservices-based application. And in this microservices-based application, I've got a number of different services and components running in order to be able to service individual requests. So in this case, it's a website to be able to view orders and place orders. And because I'm doing microservices, then it's got to be a SPA, right? So we're going to have an Angular UI. The Angular UI talks to a composition gateway or API gateway. It's the BFF, or backend for front end. So that API is explicitly designed for the one UI, and then that composition gateway will then compose multiple API calls from the backend, be able to service up that one call to the front end. And in this case, it's just using like a web API call, but you can imagine that could be GraphQL or REST or just web API. It's whatever you want to do to be able to compose all these different information from the backend, be able to display in the front end. Now, what I'd like to have happen in my distributed trace is that if something goes wrong, or if I just want to see some information about all these different pieces, that I can see just one kind of graph of calls that has all these different communications that happen. But what I'd like to have happen is not just have like the HTTP traffic as part of this picture in that distributed trace. So if my API call makes a call to a database, well, it would kind of be nice to know like what happened with that database. Was it call to the database slow? Was it fast? Did it return too many records or not enough records? What were the parameters being passed in? That could be valuable information for me if I'm trying to diagnose an issue of something going wrong in a test or production environment. So really what I want to have happen is every single one of these arrows show up in my distributed trace. The next one is going to be a lot more complicated, because this one is dealing with the writes. On the read side, it's kind of a very simple scenario usually. It's a fan out of calls, gathering information, and then pulling it back in again. But for the cases where I'm changing information or performing an action or operation in the system, well, this time I can have a lot more pieces and they could be a lot more distributed. So in this application, I've got a single Angular front end, and I click a button on the page to say place order. Well, that calls directly the sales API to say, okay, I want to place my order. But the sales API knows that it can't fulfill this order by itself. So it's going to just record some information in its database and send a message to a backend messaging endpoint to actually process the order and do its work. So this backend messaging endpoint receives a message via RabbitMQ or Azure Service Bus or whatever it might be, makes a call to a database, and now it needs to notify multiple consumers that the sale has been made, and now you need to start fulfilling the order. So initially, the sales made a call to just send a message to a single endpoint. But at this point, I want to actually notify multiple consumers. So I may use a fan out or pub sub kind of message to notify lots of consumers that this order is in. It's time to go to work, do your stuff. So at this point, I'm going to publish a message out to multiple subscribers. I've got finance subscribing, I've got shipping subscribing, and I've got customer subscribing. And they're all subscribed to the order submitted event. Now, in each one of these, they're going to perform their own business logic to do their stuff. So on finance side, they need to do two things. They have to call into a database and make a call to a third-party payment gateway. So they'll split those up into two pieces and say, how about let's first call the call to the database and send another message to myself, which is to initiate the payment process. And it's doing this because it can't put both of those in a single transaction. I can't call Stripe and talk to a database at the same time. So I'll split those up into separate operations to be independently retried or failed by themselves. So that call makes out to another API to some other third-party payment gateway that we don't own. So in that case, I want to see the arrow going into the payment gateway, but I don't necessarily have any visual. I don't have any visibility into what goes on behind the scenes. But I at least want the API call out to it. Now shipping's got some more complex logic. It says, well, I can ship my product when I receive both events, order submitted and payment succeeded. Only when those two things have happened successfully can I actually ship the order. So it's actually subscribed to two events. It's subscribed to the order submitted event and it's subscribed to the payment succeeded event. And when both of those are received, then it finally says, okay, go ship this thing via FedEx. So another message goes out the door to our operations folks to ship the product via FedEx or whatever, Kangaroo or whatever, I don't know. And then customers is just recording order information for the customer service site. And so if the customer calls in for something, they've got the list of orders there for the customer. They can go then and look up more information in other systems. So that's a ton of arrows, but that pales in comparison with the typical number of connections I have with my distributed systems. The ones that I deal with, like there's dozens of messages in some interactions, 20, 30 API calls. And so although the graph can get big, I still want to know, like when something goes wrong, or even just I want to look up what happened. I want to be able to see all these different pieces pulled together. So how do we make this happen? Well, again, 5 years ago, it would have sucked, or even 2 years ago. I would have had to very early on pick a tracing tool because all of my infrastructure had to be built towards that one specific tracing tool. But these days, I don't have to do that. I can have my infrastructure code just go against the generic activity API, and then have OpenTelemetry as the piece that's able to listen for activity events and then pump them out the door to our to whatever exporters we want. So to do this, we're going to need some packages. Packages. The first one we're going to need is the hook for OpenTelemetry into ASP.NET Core. So this is the OpenTelemetry extensions hosting project. And all this is the ability to say services.add OpenTelemetry, and then from there I can register individual extensions to OpenTelemetry, both on the instrumentation side and the exporting side. So the next thing I need to do is actually instrument my application, and that comes for the OpenTelemetry instrumentation packages. So those packages are listening to activity events via the Diagnostic Listener API, record specific interesting events, or all of them, and forward those events, batching them up over to our exporters. So that's the last piece of the puzzle, the exporter libraries. So at this point, I would choose which exporter I want. There are exporters for all of the major distributed tracing tools out there. And there's also an exporter for the OpenTelemetry API. So OpenTelemetry is also defined. Here's a standard web API, HTTP API, that if you just conform to this, then I don't have to change packages, I just change URLs. So some of the tracing tools have started to adopt that standard. And what that would allow me to do is to really just standardize on OpenTelemetry and be agnostic towards any exporters that I'd be working with. Now, it is still important that I pull in the individual instrumentation libraries. My code isn't instrumented by default. I need to opt into this because it is an operation that can slow the processing pipeline down. Instrumentation is not free. Some folks like to do auto instrumentation via logs. I've never found that works very well. It doesn't triangulate well, and if I need to add additional information, it's not that great to be able to change after the fact. And so what the instrumentation libraries do is will light on if something is actually listening to it. So I can turn it off in production and put into lower environments, or turn it on at a lower rate in production to ensure they don't degrade performance. So let's now switch over to my Frankenstein's monster of a demo application and see what we see. Okay, now this microservices application, go away, I don't need to update now, please no. This microservices application has everything inside a single solution because I'm lazy and it's easier for me to run the whole thing all at once. But in a production environment, in a real development environment, you don't have everything inside a single solution. Each one of these top level services would probably be in their own repository, maybe in a monorepo, but definitely not in the same individual overall Visual Studio solution. So I'm just making my life a little bit easier. So in each of the applications, I've added the correct packages for the hosting, the generic hosting library. So now I can say services.blah. I'm adding the appropriate instrumentation as well. So this is for ASP.NET Core. This is for SQL clients. And then for this demo, I'm actually showing two different exporters. I'm showing Jaeger and Zipkin, but there are a ton out there that you can pull from, App Insights, Jaeger, Zipkin, Prometheus, I don't know. Other Greek gods, I think, are up there as well that you can pull from and just plug in the one that you want to, if the OpenTelemetry API is not supported out of the box. So what I like to do is run through both of those scenarios, the get scenario and the post scenario, and see what we see in our exciting distributed tracing visualization. Now I have put the turbo button on my laptop, so hopefully things go a little bit faster, building and running all these applications. We'll see. Now you may notice some other packages there. I've got my library for doing messaging. I'm using in Service Bus because it's easier for me to get up and going. And I've also included a package for in Service Bus, which includes the instrumentation support for that. So out of the box, .NET Core provides instrumentation for ASP.NET Core, for HTTP clients, for SQL clients, and for Azure Service Bus. But I don't always use Azure Service Bus. Sometimes I'm using RabbitMQ, and so I don't have any instrumentation there. So what I've done is added this package, the extensions Diagnostics OpenTelemetry, that does two things. One is it is able to do the whole header to activity to header translation that ASP.NET Core is doing, as well as surface those events out to OpenTelemetry. So here we should see a dialog pop up here in a minute. It is using the full extent of my design and CSS capabilities. So prepare to be wowed. Yeah, there we go. And the first thing I'll do is look at the list of orders. So behind sales and all the other ones, pulling all those pieces together to be able to show on the user interface. And eventually this will come back. Yeah, it's running like 10 console windows, which is a lot. But it'll eventually come back with a list of that list of orders. So while that's going, what I'll do is I'll switch over to some of the other code to show you what else I needed to set up for each of these. So back in my Visual Studio, the other piece of the puzzle I had to do was in my program.cs for all of these applications, I did have to turn on the default ID format and to force the default ID format to true. Now, this is a pain at .NET Core 3.1, but this is intentional because .NET Core 3.0 and 3.1 were released before the W3C standard was finalized. And so to ensure that they didn't like accidentally switch everyone over to a different trace ID format and like screw everyone's code up, instead what it is make this an opt-in feature. So you have to explicitly turn on these things for .NET Core 3.1. Now, for .NET Core or .NET 5, those two things will be on by default, or really just the activity format. So in .NET 3.5 or .NET 5, activities will default to the standard format, so it would be good to go there. Let's see if our API finally returned. Oh, Lord, APIs are running slow today. Okay, let's swap over now to our visualization of this traces and see what we see there. Okay, so I've got two windows open. One is for Zipkin and one is for Jaeger. Now, Zipkin is like easy mode for distributed tracing. Out of the box, it doesn't have, you can run it without any kind of persistence storage. So you can just have these traces actually stored in memory versus being stored in like a database or something. But it does have plugins for like some document databases. You can store the traces in Kafka as like streams. You can store the traces in Elasticsearch and a couple others as well. For some of my just running locally though, it's just easier to run it based on just in memory, just to make my life a little bit easier. So if I search, I don't have any traces coming up yet. What I can do is go back a couple hours to show let's go back 6 hours to show a previous trace that I ran earlier, in case my slow API never actually comes up. Okay, so what is this trace? What does this span? This is the initial GET request to orders to be able to show the list of orders on the screen. And when I was running earlier, it was pretty, that was what, almost a second or 660 milliseconds. So that's not too great to be able to turn all that information. But what we can see is that it's actually pulling together the different services in one single visualization. So it starts off with that call to the composition gateway. Then the composition gateway is composed of 3 different other API calls. So I've got a call to the sales API, I've got a call to the customers API, and I've got a call to the finance API. And then each of those API calls also makes a call to a database. So we can see as part of the trace, the actual calls to the databases as well. Now, the other piece of the puzzle here is, well, I want to see some information about each of these different operations. So when I click one of the operations over here on the right is some of the additional tags as part of that individual operation. So this is what OpenTelemetry actually adds on top of the activity information that comes just kind of standard from .NET Core. .NET Core doesn't add any additional information about what the request was doing. And so ideally, I don't just have like an API request is made. Great. I want some context about what that operation was. So that's what all these different tags are. It tells me the host information, the method, the path, what the status code of if it's good or not. Yeah. And then this is the incoming API call. Now I have the second one, which is making the API call. This is the receiving one from the sales side. So receive that sales API call, and I can see the additional information we have there. And then we can click down into the actual database call that it made. So over here, this is now a database kind of trace plugging into SQL client to be able to show SQL information. So this information here is the actual statement being used inside of that SQL call. Now it has scrubbed out some of the identifying information, so I won't see parameters. If I want more information like that, that's when I start to switch over to a log tool to see the individual set of details for that one call. So I can see that it's got all the API calls, all of the database calls, all in this nice hierarchical view that plugs everything together. So if I compare this picture with Yeah. So it looks like this, right? I have the incoming call, the one call, that was the top level operation. We have the second level call, and then 3 calls to 3 databases. Well, that's exactly what we have here in one single view. Let's look at Jaeger, because Jaeger is a bit nicer. And I'll go over to the composition gateway, looking back at the last 6 hours and find those traces. And there we say, oh my God, it finally, oh no, that was from 5 hours ago. Yeah, the first one took 5 seconds, so this one might still be taking a while to return. Okay, so let's look at the fast one. That's more interesting. So yeah, it's a similar kind of view, right? We've got the overall call. We have the sub calls being made into the different pieces of information. I can see individual tags about what those look like. Jaeger is a bit nicer looking. You can kind of see that it's a bit cleaner looking interface, and its searching capabilities are a bit nicer as well. So that was the get operation. Let's see if my UI ever returned. Did not. I'm going to refresh to see if it ever comes back. I don't think it is. That's okay. I've got my old traces. So in my more complex example, where I had all these different things going on all at once, that starts to get now super, super complicated of all these different pieces getting plugged together. So this is where it can become a little bit difficult to even find this trace versus something else. So after I show this trace, I'll show you ways of enhancing the output inside of those different traces to be able to have more contextual information for your individual trace, distributed traces. So let's find this one now. So this one starts off with the Angular UI calling the sales API. So let's go back over to Jaeger, because Jaeger is nicer, and go back up to the sales API. Back 6 hours and find the traces. Okay, here's one that is for creating an order. And you notice now that I bumped the size up a little bit. It's got a lot more services it's talking to. So each of these little bubbles here are the different services that were associated with this initial request. They were part of this overall trace. If I click one of those, oh, yeah, this is a lot more complicated of things going on. So let's collapse a couple of these down to kind of walk through these steps one by one. So we said the first thing was, there's an API call to say create an order. So that's this first one we have here. I can see the tags as part of it. You notice it doesn't have like the payload as part of it, so it's not including that level of detail. That's intentional. This tracing tool is not meant to replace your logs. Your logs are still there to get the details, but the problem with logs is that is a part of cardinality of the data. There's a ton of data in your logs, but how do you find the right data? That's really what the traces are intended to do. So if, for example, I saw something going wrong with this call, then what I would do is include the span ID, which is right over here, in my logs. So if I include the span ID in my logs, I could search for that span ID in my logs and now just have just the logs for that one operation in my trace. So Sales API sent a message via RabbitMQ. That's the send we have right here. And I can see some information about it. It's a producer, there's a payload size is 34 bytes. And then I have a consumer that's going to receive that information and now process it and publish the message out. So as part of this, we should expect to see a couple things: talking to a database and publishing a message. Now, inside of that, I've actually got a lot more information going on here. So what I've done in the, this is in Service Bus I'm using to be able to record this information. I've enriched the tags on the activity with a lot of contextual information so that if I'm someone that's needing to diagnose something wrong, I've got a lot more information for me. So what I've actually done here is, in my configuration, I go just look at one of my endpoints. We will see that after I call add OpenTelemetry tracing, which is the services dot from the extensions hosting. I had the exporters for Zipkin and Jaeger, which really just need to tell them the URL to point to. Then I have the different instrumentation. And one of the things I've done for demo purposes is to capture the actual body of the messages. So probably not something you'd want to do in a production environment, but for demo purposes, as well as for like dev, like any low environment lower than production, you can flip that on so that you can more easily diagnose a bug in a distributed system. So back in my UI, I can see like the full message body as part of that. So all the other junk that might be part of this. So it's one of these things, a submit order command, sure. And then we can see, what does it do next? Makes 3 calls to the database. So I can see 1, select the product ID and name, sure. 2 other calls to the database. And then finally down here, it has a publish the order submitted event. We saw that there were 3 subscribers to that event: the customer service, the finance service, and the shipping service. Now, shipping didn't do anything at first because it was waiting for that second event to come in. So as part of its information, we just see, yep, it received this message that said this order has been submitted. But the other ones are more complicated. So customers was doing some database stuff to insert some information about the customer, and then it was done. And the finance did a couple things. First, it saved some information into its database. So it said, save, yes, save the data to the database, or give the information out, and then save the data to the database. There we go. Yeah, insert into this some stuff that it's done. All right. And then it's going to publish a new message that is, hey, I have, oh no, it needs to actually submit the payment. So this one is going to send a message to itself to say, I need to charge the customer. So this message is initiate the payment process. And then down here, it's going to make a call via API to this other third-party API, which is just localhost, but you get the idea, to make the payment. Once that payment is successful, then I publish a message saying payment has succeeded. Shipping receives it, receives a message and says, okay, now that shipping is good, I'm going to send a message to the operations to ship with FedEx. Here we are. And then IT ops receives it, operations, and saves some information that said, yes, I'm going to ship this package to the customer. So that entire complicated graph of all those different services together can be represented in one single distributed trace that we see here. Now, these tags were done automatically by our really just by the underlying exporters from OpenTelemetry, putting all this information in there. But if you wanted to add your own information to that, let's say we have some additional context information that's relative to like our SRE folks, so that when they're trying to diagnose a problem, they can fix it without worrying about like having to go back to the logs or something like that. So inside any of my API calls, if I start to have like some contextual information, like this one, for example, I say, ooh, I got a customer ID. Then what I could do is go to activity.current. Yes. .current, now that's a current running activity. So in this case, it'd be the ASP.NET Core activity. And then I could say add tag, and I could put in a tag in here. So I could be like customer.id, and I give it a value of customer ID. So now, when we see our traces show up, for this operation, it will include the customer ID in my trace, which means inside of Jaeger, instead of just like blindly going around and like, I don't know, then what we can do is actually search by tag and say cust.id equals 3. And now we'll pull up all the spans with that customer identifier. The last piece we can do is if I have additional context information that really needs to flow to all of my traces, tags are only associated with the current operation. There's another piece which is called baggage. Now, baggage is part of a new emerging standard. which is designed to attach additional context information to all of the communications that get the initial trace context identifier. So in this case, add baggage will actually flow that baggage information to all of the child activities. And when I make calls out the door via HTTP or via RabbitMQ or whatever it might be, then those information is put together into a single header that then flows out the door to be consumed on the other side. So this would mean that that customer ID would show up for all of the subsequent spans and operations and activities for this customer ID. So that's pretty cool. We use that a lot in my clients to be able to quickly triangulate, like someone has a problem, okay, give me your order ID. I can quickly see all of the traces for that order ID across all the actions that users performed. Pretty rad stuff. So that was distributed tracing made easy with .NET Core. When we're looking for .NET 5, the only thing we need to update is to remove the default the activity ID format from W3C because it's done by default. Otherwise, it works exactly out of the box. Now, the other cool thing is that the activity API is not actually tied to .NET Core. It targets .NET Standard, and so classic ASP.NET Web Forms also has this tracing stuff built into it as well. So they have actually updated those to use this standard. As long as you just update this out-of-band system diagnostics package, you'll get the new W3C tracing support out of the box. So really cool stuff. So we have a couple minutes for, well, -1 minute for questions. So I'll just answer a couple of those real quick. If I don't answer them in the next 30 seconds, then I will answer them on the Slack channel. The first one was, does the .NET Framework 4.7.2 support OpenTelemetry? Yes, it does, because the system diagnostics and OpenTelemetry APIs target Net Standard 2.0. So that means it actually supports .NET 4.7.2. Now, depending on the runtime, that may be a little different. So classic ASP.NET versus ASP.NET Core, you'll have to check the details in each of those. The other questions were over, so I'll take the rest of the questions and move them over to our Slack. Otherwise, have a great morning. It's Wednesday, and I'll have a great Tuesday evening. So thanks, everyone.